Hi, today we're going to do rockets. And I'll start out with a disclaimer. We're going to be dealing with flammable compounds and oxidizers. We're going to be building rockets. And so if you're uncomfortable with the chemistry or unfamiliar with some of the handling of these materials, you probably don't want to do this, or you want to get somebody involved who has some experience, because safety is an important thing to always keep in mind with any kind of project that we cover here. Now, there have been a lot of questions after previous videos about how we determine what we're going to cover in our projects. And an overriding consideration is it's got to be something that we want to do, because we spend a lot of time and effort on our projects. And if you're not enjoying what you're doing, you're not going to put in the amount of effort necessary to do it right or to cover it well in a video. Based on the fact that we like what we're doing, we also find that some of these projects are relatively large and will often lead to derivatives. For example, a couple of years ago, we built a large drone, and we're struggling to obtain the large rotors that were necessary for that drone. And so we actually built and covered in a few videos the construction process behind building your own rotors. Last year, when we got into speakers and acoustics, and I built the Voight tube that you can see behind me here in the lab, this led to a need to do a lot of analysis of the acoustics, and so that led to the construction of our small anechoic chamber upstairs. Last year, we also did a video on magnetohydrodynamics. Complicated word, simple process. When you take a conductor and you move it through a magnetic field, you will generate a current at right angles to the movement and the field. Now, that conductor can be a wire, as it is in a generator or a motor, but it can also be a conductive fluid. And so we did some testing, and we demonstrated a very small version in that video about using salt water or seawater to generate the power. The difficulty is that an ionic liquid, a salt liquid, a dissolved salt, has a relatively low conductivity. And so in order to compensate for that, you either need a very powerful magnetic field, and or you need to move the fluid very, very quickly to generate real power. We struggled to produce more than a couple of watts. And so we then began to look into the idea of a gaseous conductor, because a gas in the plasma state with ionized ions, or ions and electrons, is very conductive, and it's actually easier to move it at very high velocities. And that type of process is actually not new. It's been around for decades. NASA has looked into it, and there are actually pilot programs at natural gas-fired power plants where the very high temperature exhaust from their burners are blasted, often at supersonic velocities, into the boiler where it boils the water to create the steam to produce the turbine motion that generates the power. But on its way in, it's in the state that could potentially generate power, and it does. The problem is, even at those temperatures, 4,000 or 5,000 degrees, there is really very little, if any, ionization of the particles. A lot of people think that a candle flame or an oxyacetylene torch is a plasma. It is not. The high energy kinetic impacts of the particles, of the molecules and the gas and the atoms, will elevate or stimulate some of the outer electrons on those atoms and move them up in an energy state around the atom. And when they collapse back down, they settle back down, they'll give off photons and give off light. But it's not enough of an impact to literally rip the electron off and create a positive ion and a negative electron, which is a plasma. So they're not conductive. However, there's a way to cheat. And that is, if you add dope at a small amount of another element that has a much lower ionization potential than the typical combustion products that are used in these flames, you can enhance that ionization. And we'll get into a lot of detail on the tricks and the techniques as to why the sort of perfect atom for this purpose is potassium, the alkali metal. And so, not having access to a gas-fired power plant, I thought, how could I get a very high temperature, very high velocity gas or exhaust that is enriched in potassium? And the obvious candidate is a potassium nitrate solid rocket engine. And so that's why I began to investigate rocket engines, because yes, you could go out, you could buy a small little model Estes rocket or Aerotech rocket, but they're very small and they may not allow you to tweak the potassium and may not allow you to tweak the parameters of the engine. And because it's not that difficult to build a solid-state rocket engine, I started getting into it. And that's why, even though later on we're going to peel off and take some of these rocket engines for the MHD project, I thought I'd cover in a couple of videos here the actual construction and principles behind rocket engines, how they work, how you can make some yourself, and basically quantify them to get an idea of how the performance is. Now, there are basically three different types of rocket engines. There's solid, there's liquid, and there's hybrid. The hybrid uses a solid fuel most of the time with a liquid oxidizer. And in the case of a solid rocket, obviously you mix the fuel and the oxidizer together ahead of time. And in the liquid, you add them together in the combustion chamber to produce the thrust. We're going to be covering the solid rocket engines, and we're also later on in a video, actually the next video, we're going to cover a much more sophisticated and actually state-of-the-art hybrid rocket engine. And then I'll go into more detail about the test rig that I've used to not only support the rockets during their test safely, but also to quantify the output in terms of thrust, peak thrust, and total output. We'll get into that in the future video, but what we're going to focus on today is some of the basics of what makes a rocket engine work and some tricks and techniques to building a very sophisticated, very nice looking, and potentially very powerful solid rocket engine. Now, if you're interested in rockets, you might want to take a look at Scott Manley's channel. He's a great channel about, the very highest end of state-of-the-art, the Raptor engines. Or you might go back all the way to, say, the old King of Random, where at a kitchen stove he took some table sugar and some stump remover and he produced a sugar rocket that did fly. It does work. There's a whole spectrum of potential levels of sophistication in building rocket engines, all the way from the low end to the high end. And there's a lot of videos out there. What we're going to do is I'm going to show you some tricks in building a solid rocket that produce a very powerful, sophisticated rocket, but are still easy to do. And so to begin with, even though this is a technical channel and most of the audience here are pretty technically savvy, I'm going to go through really quickly the reasons why a rocket engine works. And some of this may be a little bit of a new way of thinking about it. Now, when a rocket engine moves, obviously it's a relative force that's produced by the relative transfer of momentum. You've got the gas going out one end and you've got the rocket moving in the other end. But effectively, a rocket engine, no matter what the form of the fuel, is a pressure engine. It's driven by a pressure differential. So even though the rocket's exhaust looks blindingly hot, thermally very, very excited, it's pressure and pressure only that's actually moving the rocket. If you imagine a room like this, filled a little bit above atmospheric pressure, the pressure on all the walls is the same, obviously. The force against all the walls is the same because the surface area times pressure is the same. So the room doesn't slide across the backyard. However, if you open up a door, let's call that the nozzle, and you allow some of the gas to move out of the room, the gas particles moving in one direction are what you think of as the rocket exhaust, but what produces the mechanical force against the rocket to move it in this direction is the net difference in the surface area. Consider the door the nozzle. And so the wall that does not have the door in it has a larger surface area than the wall that has the door nozzle in it. And so it's the differential area times the same pressure that produces the force, the net force that moves the rocket forward. And that is the lowest amount of force or thrust that a rocket engine can generate if it's just spewing its exhaust out of an orifice. It's just a flat plate with a hole in it. However, because that gas is at a higher pressure than the outside, if it's in space, it's a vacuum. If it's on the surface of the Earth, you have to compare it to atmospheric pressure. But nevertheless, because it's expanding outward, as it moves away from that orifice, as it spreads out from that orifice, it's not only moving parallel to the rocket engine, but it's also moving at all angles, as you can imagine, all the way up to a 180-degree hemisphere. And as a result, you're losing a lot of potential energy, a lot of momentum from those particles that are going off at an angle. So what you can do is if you put a pair of reflector plates in that expanding gas, so that rather than letting them go free, you redirect them parallel to the axis of the engine. Those plates will be pushed forward. And if those plates are rotated in space all the way around, you have a nozzle. And it's that nozzle that can enhance the thrust of the rocket as much as twofold in a vacuum, that you will always include a rocket nozzle in order to enhance the output of a rocket engine. Now in space, because there is no outside air pressure and that gas is going to continue to expand forever, you would want a nozzle that's theoretically infinitely big in order to capture that last little bit of potential thrust. There are practical reasons involved, but that's why you'll see that rocket engines that are designed for the second and third stages of high altitude rockets always have much larger nozzles, because they can take advantage of the fact that the gas is going to expand farther. Closer to the surface of the Earth, as that gas expands and its pressure drops, because it's a moving stream of gas, just like the gas that comes out of a propane torch, what will happen is that that moving gas, because of Bernoulli's principle, will actually have a lower than atmospheric pressure, and that's how it draws air into it to create the mixing that produces the flame. So eventually, as that gas expands out far enough, you're not only going to reach atmospheric pressure, but you're going to drop below it. And at that point, the flow of the exhaust can separate from the nozzle. There's no reason to have the nozzle any bigger. You'll actually destroy the nozzle with turbulent effects. And so there's the maximum size to the nozzle on the surface of the Earth, and that has to be balanced against the pressures and a lot of rocket science type of equations to determine what that is. We don't have to go there, because it turns out that the value of that nozzle effect, most of it occurs very early on in the expansion. So if you take a nozzle like this one that I built out of graphite, and you have an orifice that's about 1/4 of the final area of the nozzle, you're going to get about 70 or 80% of all the potential additional thrust you'll get from that nozzle. So you don't have to get real fancy and produce bell nozzles, just a little bit of a cone that roughly doubles or slightly more than doubles the orifice or the nozzle or the limiting orifice that allows the gas out of the engine. Now, solid rocket motors have a couple of advantages over liquid and hybrid rockets, and that is they're super simple. You mix up everything together, you do that in the shop or the lab, and then once you've done that, you don't need pumps, you don't need valves, you don't need any kind of control system. You just light it and you forget it. Another advantage is because the rocket fuel is often constructed in what are called grains. Kind of a weird word, because you think of a grain like a dust grain, but the grains for large rockets can weigh more than I do. It is the fuel chunk that sits inside of the cylinder of the rocket engine. And it will often have a central hole in the middle, which is where the flame front occurs. And as that flame consumes the rocket fuel, you call that the regression of the fuel, the regression rate. Eventually you get to the outside and then you're out of fuel. Because this is has a poor thermal conductivity, the chamber that is actually holding the rocket grain or the fuel grain doesn't have to resist any thermal loads, because until you're just about ready and out of fuel, this remains cool because of the presence of the fuel. But it does have to resist the pressures, and so it has to be strong, but it can be something that is thermally sensitive, like a composite, which is nice to work with, inexpensive, and light. Disadvantage of a solid rocket engine is, number one, you're mixing everything together. You've got an oxidizer and you've got fuel together, you've got a firework. And so if it turns out that you get a spark, this thing could ignite spontaneously. It also means storage and transportation are very limited. That's why you often can't buy large rocket engines online. The other disadvantage is it has a relatively low punch. The amount of power that you get per gram or per pound of a solid rocket engine is substantially less than out of a liquid or a hybrid engine. But because of the simplicity and the light weight of the container, the difference isn't quite as bad as you might think, but it's still not sufficient to make up the difference. And so that's why high performance, large projects will always go to hybrid or liquid engines, simply because of the fuel differential. So that's basically the basics. And so now what I'm going to do is I'm going to go next door and I'm going to show you how we built these, and I'm also going to show you my secret rocket fuel. Come on, let's get going. So, just so you get an idea of how much effort went into the formulation, this represents about half of all of the samples that we had played with in order to come up with what we found to be the optimal formulation that we're going to cover with you. And so, before I get into the actual mixing and the percentages of the material, what I'm going to do is show you how you set up the motor in order to be able to be filled with fuel. And to begin with, I'm going to recommend a site called Rocket Motor Parts. It's a nice online site that sells a lot of the parts that you see down here on the table. And what's nice about it, even though it's not the least expensive method of building a rocket, is all of the parts fit together. So you can buy nozzles, you can buy tubes, you can buy liners and rings and all the things that you would need. And you got to remember that time is money. And so if you can save time, it's going to make the building, especially when you're first starting out, a little bit easier to do. As you get more experience, you might want to cut some corners and use different materials to save money. Nice thing about the tubes that we obtain from them is these are spiral wound fiberglass tubes. And spiral wound means that when they're fabricated, they actually wind continuous filaments of fiberglass around the mandrel to produce a very thin and extraordinarily strong tube. The strength of this material is equal to steel, but because of the fact that it's fiberglass, it's extremely light. They even make a carbon version, which is slightly stronger and even lighter, but this is enough for our purposes. And in addition to coming in multiple different sizes, as you can see here on the table, if you look carefully at the end, you will see that there's a little gray appearance to the end of the tube where they have milled in some grooves, which will help to retain the nozzle as well as the plug that we put at the other end. And all of that comes right from the manufacturer. So again, you don't have to do this yourself. It's a nice way to get started. Now, the tube itself is going to have a plug at one end, as you can see in this finished motor here. That plug is what's going to keep the gases inside of the motor when the gases are coming out the other end of the nozzle. And so to fabricate that plug, what I'm going to do is I'm going to fill this with some, you guessed it, epoxy. And to do that, an easy way to set that up so that you produce a very nice plug is to get some of this disposable foam board. This is PVC foam board. It works very well with hot glue, like we used in the rudder video. I'm going to take a little bit of hot glue here and I'm going to put a couple of dabs on either side of this motor that will basically fix it in place so that it doesn't slide around. And these don't have to be big, just enough to kind of hold the motor down during the subsequent fabrication. Then we're going to wait about a minute, and this stuff will firm up enough that we're going to be able to finish the entire seal and produce a watertight or epoxy type dam that's going to get on the inside of this tube but not around and out the other end of the tube. This doesn't take very long because this stuff cools off pretty quickly. Let me show you now that the motor is probably pretty well fixed, that you can apply this very imprecisely all the way around, and I'll do the other side for the other camera so you can get a better view. And again, be generous because you don't want this to leak. It can create a bit of a mess. And I'll come around on this side and just press it against both surfaces, sort of at a 45. And you're assured of getting a very nice solid seal. Now within about a minute, this is going to be hardened up. And then what we're going to do is we're going to go ahead and we're going to fill this with epoxy. Now you want to use a slow set epoxy. I'm going to show you the Reka that I like to use because it's so inexpensive and very reliable. And the slow set epoxy is necessary because you're doing a volume cure. And when you have an exothermic reaction like this, if you use something that cures more quickly, it develops a lot more heat very quickly and it can actually combust, or it can damage the epoxy and the tube that it's in. So a slow cure mixture, and we can calculate that we want about a centimeter of thickness. So with a tube that's 1 inch ID, or 25.4 millimeters, you can calculate that you need about 7 or 8 milliliters of this epoxy. So we're going to mix up some of this, and I'm going to show you how I fill this. And we're going to go ahead and we're going to put in 25 grams of this. Now, the only reason I'm using these numbers is that they're easy for me to remember. This is a 2-to-1 mix of epoxy by volume, but it is a slightly higher amount of resin, of hardener, because it's lighter by weight. So now I'm going to add 15 more to this and bring this roughly to 40 grams. Now, as I've always told people in epoxy videos, you want to mix for a solid, honest 2 minutes minimum. Now once this has been blended up, I've got plenty of time to work with this, and as you'll see through the entire video, the entire process of making one of these motors will take probably about 2 days because of all the different drying steps that you need to use. But because of the fact that the drying, the actual work involved is only a couple of minutes at a time, you could probably make as many as a dozen motors in the same amount of time as you make 1 or 2. So once you get good at this, the fact that this is going to take 2 days is not really that much of a drawback. Now the trick by using the syringe is that you minimize dirtying the inside of the tube because you don't want to get any stickies up above the plug. The problem with that is that that can interfere with the placement of the nozzle later on. You want to be kind of neat at this stage. Now the epoxy you can be neat enough with that we can just get away with using a syringe and kind of a careful injection. But when you go beyond there to add the fuel, you're going to actually want to use a little protective liner to prevent you from getting any epoxy on the upper part of the tube. Now what I'm going to do is insert this down, and I've got 7 milliliters that I'm going to put in here. And we just squirt it in the bottom and allow it to flow out and fill up those grooves at the other end of the tube. Okay, so now that this thing is going to have to dry overnight, I went ahead and I made one of these yesterday, and if you look carefully in the bottom, you'll see that it's almost mirror reflective. Not sure that that will show up very well. Maybe it will with the flashlight. But you can see that the epoxy forms a nice flat plug in the other end, and it's much lighter than the concrete that you typically use in some of these PVC rockets. Now we're going to need to fill this with fuel. And the point is, we want to fill it up so that the nozzle, which is going to be inserted in the end of the rocket motor like this, is going to be retained. Let's see if I can get this in. It's a very like slip fit, but it's very close tolerances here. When I place the nozzle in here, I'm going to want about half of the nozzle to be exposed. And what that means is that when we pour epoxy in above here, like I did on this motor here, that epoxy will harden and form a ring that will retain the flange to prevent it from being extruded or pushed out by the pressure of the inside of the chamber. So we're going to want to insert this a certain distance once the fuel is in. Complicating that is the fact that when we form a fuel grain, we want that inner hole. And it turns out for this particular application, these epoxy mixing nozzles, I've got everything related to epoxy, are just about the right diameter and length for this particular size motor. And so when I've got the warm but then soft fuel in there, I'm going to insert this into the center of the fuel, creating that central port. And then when I pull this out, I'm going to end up with a nice fuel grain. But what that's going to do when it goes into the fuel, it's going to raise the level. Now I've calculated this out, and you can do that yourself depending on what type of core you're going to make. But it will raise the level of the fuel, and you need the level of the fuel still to be low enough that you're going to get about half of the nozzle retained inside of the end of the chamber. So it's a little bit of paperwork math for any particular engine. But when you put everything together, you can calculate a distance. And when you come up with that particular distance, you can take some of these paper liners that are available from rocket motor parts and draw a line. I've got this little dotted pencil line that represents how far I'm going to insert this into here in order that when the fuel rises, I end up with a depth of penetration of the nozzle that's just right to retain it at the right level. So I use this to measure how high I should fill this with fuel. And I also use this as a way to keep the outside clean so that when I want to put the epoxy in there, I'm not gluing fuel also, and it keeps it possible to put it in the nozzle. So now the next thing we need to do is we need to end up building or making the fuel. So let's get on to the chemistry, because that's really the fun part. A sugar rocket, classically, the type that King of Random made years ago, is based on table sugar, sucrose, mixed in with potassium nitrate or stump remover or saltpeter. And the optimal ratio, as we talk about in a lot of our chemistry videos, is the stoichiometric mix, which means just enough oxidizer, just enough fuel. We burn all the fuel, we don't have anything left over, we get the most amount of energy per gram out of the total mixture. That stoichiometric mixture is about 3 parts oxidizer by weight and 1 part sugar or organic compound by weight. Problem is, you can't get that much of the solid salt oxidizer into the sugar to form anything other than something that's like plaster. As you drop it down to what is generally considered to be the optimal mix, which is 65 parts to 35 parts, roughly 2/3, 2 parts to 1 part, you're almost as good as the stoichiometric mix in terms of total output, but it's much easier to blend it. And that's the ratio we're going to use. So when we make up 100 grams of fuel mix for this particular rocket, we're going to use basically 65 parts of oxidizer and 35 parts of sugar. Now, in order to make a sugar rocket, because sucrose is melts at a very high temperature and tends to burn, you do it based on what's called the recrystallization process. You take water, doesn't matter how much you want to use, you use water, and you'll put the oxidizer and the sugar together into the pan and you'll mix them up. You're making a candy. The water, by dissolving the compounds, gets the 2 particles very close together, and as you heat it and you're cooking off the water, it becomes thicker and thicker and thicker. It's like you're making candy. The end result, though, is still very thick, and you have to get to some pretty high temperatures to drive off enough of the water that it doesn't interfere with the performance of the fuel. There is a better material to use for sugar rockets than sucrose, and it's based on a sugar alcohol called Sorbitol. This is a food product. You can get this for health food, and it's actually a sweetener that doesn't have any calories. Your gut can't digest it. So it tastes sweet, but you won't get any calories from it. If you have a little bit, it can make your food taste sweet. Have a little bit more, and it's an excellent laxative, so you don't want to push this too far. Nevertheless, it has a very low melting point, and so because this melts at such a low temperature, around 100 degrees centigrade, we don't need to use the water. And so we can use this as the liquid matrix to hold our fuel. So that's what we're going to do to mix up the fuel. 35 parts or 35 grams of this is where we're going to start. Wow, to the milligram. Now, because the sugar will melt, you really don't need to grind this up ahead of time because it's just going to liquefy. However, if you do grind it, it makes the pre-blending that I'm going to show you in a second work a lot better. So I'm going to take this little coffee grinder and I'm going to add the 35 grams of the sorbitol, and we're going to give this a little bit of a grind. So a little bit of noise here for you headphone users. You only need a few seconds. It doesn't take very long. Now we need 65 grams of an oxidizer, and typically you would use just potassium nitrate. However, if it turns out that you use a little bit of another oxidizer, you can improve the performance of the fuel, because remember how I said in the other room how a rocket engine is a pressure engine. It's not just a heat engine. The heat creates the high pressure gas, but you need gas. And because potassium is effectively an alkali metal, if you use an oxidizer that itself contains nothing but gas, let's say, for example, ammonium nitrate, or you were to use ammonium perchlorate, this will actually increase the performance of the engine because we produce more gas molecules that can be exhausted out the back. In addition, if we use the ammonium nitrate, it will actually soften or melt around the temperature of the sorbitol and improves the viscosity. It actually makes it a little bit easier to pour. If you use too much of either of these supplements to replace some of that potassium nitrate, you will slow the burn down. You'll actually decrease the regression rate, so you don't want to go too far. And it turns out you don't need much, because if you add just a few grams of this, you'll thin it out. And if you add a lot of grams to this, you'll not only thin it out and create a slowing of the reaction, but this is very hygroscopic. It will attract atmospheric water, and your fuel will get pasty and damp and sticky over time if you use a lot of this. So what I discovered is that by using 61 grams of the potassium nitrate and just 4 grams of the ammonium nitrate, you get a great mix that's thin, high performance, and it doesn't attract water. So that's what I'm going to mix up here, 61 plus 4. Now I'm going to take this blend and I'm going to grind it up in a different coffee grinder, keeping the oxidizer and the fuel apart. And we're going to bring this down to a much finer powder. Now the trick is we're going to take these two materials and we're going to pre-blend them before we hook up put it on the stove to cook it. So we're going to put the 65 grams of oxidizer in here, and we're going to put the 35 grams of fuel in here. And we're going to blend these things up by hand. It's a very easy way to do this. Just take a little plastic, rip it off, put a little rubber band around here like this, and then what we're going to do is just spin it around. Now something you might notice here while I'm mixing this is I'm using cast iron. Now the advantage of using cast iron is that it's a great pan, it's inexpensive, and it's nice because it distributes the heat from the burner so you don't get hot spots. But it also has a lot of thermal inertia. It's just heavy. And as a consequence, when we take this off the burner and we're filling the rocket, it doesn't cool quickly and then thicken up. And that's why I like using this for all the mixes. Now that this has been blended up, we're going to simply pour this into the pan, trying not to spill too much of it on the floor. And then we're just going to let it melt. As you can tell, I'm not using any water. In addition, because this melts at such a low temperature, I can actually use plastic spoons to do the distribution. They won't melt. It's kind of nice when you're working with rocket fuel that you're working at a lower temperature. It just seems like a good idea. Now I like to use wood to mix this. Again, you could probably use metal, but I don't want to create any sparks, and it's cheap and disposable. And this has just the right curvature for my particular pot that it'll get into the grooves, and that's why I use these sticks for mixing. I've also used the spoons, but they're a little too pointy. So we're going to spread this out to distribute the heat over the fuel, and this will take a little bit of time. But eventually you'll start to see the bottom become a little bit sticky as it's beginning to accumulate or gather some heat off of the pan. Now a couple other warnings. This is an electric heater. You absolutely do not want to use flame when you're in contact with this. Now as you can see, this has become very smooth, very creamy, and very low viscosity. But we can improve that even further by the other secret ingredient, and that is glycerin. If you use 1 cc of glycerin added to this, and you do that at the end, 2 to 1, this will thin out the mixture, doesn't seem to affect the burn at all, but makes it a little bit less viscous and easier to pour. And like I said, I'll try to be relatively neat, although you may get a little bit of spillage on the outside, but because this is water soluble, you can just wipe this down with a wet towel when you're done. Now I don't know if you can see it because I'm using the guide to hold it. I'll try to do it above there so you can just sort of see how it pours, but I'll probably make a mess by doing that. But you can see it just dribbles in. And then actually, before I lose this fuel, I'm actually going to take what I have remnant here and I'm going to put it on my aluminum foil. And that's for a little demonstration I'm going to do in just a little bit. So I want to do that before this gets too warm or too cool. And as you can see, the spoon is still intact. It's not melted. It's not softened. And this is very easy to clean out. You just rinse this in the sink and you get a nice clean pan to work with. And if I can, I'm going to try to remove this liner. Oh, actually, let me see if I can show this to you. You can see how it got to the bottom. See what it looks like? I don't want to tip it too much so it pours over the side. But it's right to the bottom of the liner. And then if I grab the tube, which is actually quite hot now, it is about 100 degrees centigrade, and see if I can pull this out. Then I'll show you the tube again, show you that it stays nice and clean and has a nice level.
Do that again. Good.
Now what we're going to do is we're going to take advantage of the fact that because the fuel is soft, I'm going to take this and create the inner part of the grain. Now the problem is, even though this is polyethylene and it's very slippery, if you don't grease it, you end up with the fuel sticking to the outside. So the little trick that I've discovered that really makes this work nicely is you take a little bit, this glove is getting all sticky, let's go ahead and replace that, with a little bit of Vaseline. And because the fuel is water soluble, it won't dissolve the Vaseline off. So you just take a little fingerful of the Vaseline and smear it up real nice. Get it nice and greasy. Now you've got probably, almost 20 minutes, half an hour, before the fuel becomes too rigid that you're not able to put this in. But right now, it'll flow very nicely, and the level will rise as I do that. Now I don't know if I can show you that. Maybe if I bring this over. Now if I push this down, just like this, straight down to the bottom, it's viscous enough to stay vertical. And when this cools, we can just wiggle it, spin it a little bit, and we can pull this out, and we have a nice fuel grain. Now, we're going to do the same thing again, but we're actually going to build a larger motor. And the only difference between building smaller and larger, beside just more of everything, is it's easier. Because of the scale of everything, it's just easier to get the fuel in, and it's easier to fit things. So you're going to find that this, as you get better at this, you're actually going to find that it gets easier and easier. Now, one of the things that you'll find at Rocket Motor Parts is that they're limited somewhat in the choices that they have in the larger rocket engines for nozzles. And so therefore, rather than the small nozzles, which are about $3 each that I'm using for these motors, you can't really buy the larger motors, the larger nozzles made for the 38 millimeter tubes. And so what I did is I actually bought a rod of graphite and I machined these nozzles myself. And it's nice having a lathe because you can put these things together relatively quickly. And unlike Ben over at Applied Science, who found that working with graphite was very, very messy, I discovered that as long as you keep the velocity of your cutting tools way, way down, you don't churn or move this stuff up into the atmosphere, it just sort of settles. And by just using a vacuum cleaner, being careful to keep your velocities down, this was very, very clean. And although this is reported to be somewhat abrasive and you want to use carbide tools, tungsten carbide tools, I found that after 5 or 6 nozzles, the tools look flawless. So you can probably produce a lot of these nozzles. And the other thing nice about graphite is that it is extremely resistant to heat in a non-oxidizing environment. And as I described before, we're fuel rich. We're kind of compelled to be there simply because of the thickness of the material. So this is almost impossible to melt. It's relatively easy to make. It's relatively inexpensive, and I think it looks kind of nice. I think it did a pretty good job. Anyway, the other issue is that the liner that you can get a lot of cardboard tubes for, online or at McMaster Car, you can't find one that fits very well here. So I ended up turning down a thin-walled aluminum tube with a little retaining plate. And so in order to keep the fuel to the right level, I ended up using this aluminum liner to protect the upper end of the tube when we fabricate this. In addition, I can't find the right size epoxy nozzles for the core forming. And so I just got a thick wall plastic tube, and this is made out of Delrin, and it's very inexpensive, probably about $3. And then what I did is I ground the other end, the one end of this, to make it a little bit pointy, and then got a very loose fit aluminum rod that fits in the end of this very loosely. And then with a drill stop here, just insert it all the way down, and you end up with a nice pointy plunger that you can push into the fuel. And greasing this up, we're going to use this to form the core inside of this larger engine. Now, larger engine, more fuel. More fuel, I have to go to a different scale because simply my other scale only goes up to 50 grams. So we're going to get our pot, a bigger pot now, and these come with nice little, what do you call it, spouts that allows you to actually literally pour the fuel right in, so it makes it very easy to work with. So we're going to measure out 2.4 times as much fuel. We're going to make 240 grams for this motor, and so that means we're going to need to use 84 grams of the Sorbitol. So now I have 84 grams of the Sorbitol. We're going to put it in the Sorbitol coffee grinder. Now we're going to need 156 grams of oxidizer, or 146 grams of the potassium nitrate and 10 grams of the ammonium nitrate. All right, we now have 156 grams of oxidizer. So we're going to put this in the oxidizer coffee grinder. Yeah, it's starting to warm up in there. Now, I'm going to come over here. I'll bring this actually where this was. And if you look at this, you can see, if you touch it, that it still moves. Now I'm going to just play with this a little bit just to make sure that this is going to work. And we're just going to kind of ooze it out of the hole, nice and slow. Seems to be coming pretty well. There. That's what you get when you use the Vaseline. It's nicer. And if you look in the bottom of the rocket, you can see
a little bit up. Yeah.
A nice grain. And now what we're going to do is, because we want to fill this with the epoxy, what we're going to end up doing is I'm going to use some RTV. This is a rubber. And I'm going to put a little bead around the outside of this in order to form a seal so that when I put the nozzle down, the epoxy doesn't drip around the nozzle and get into the central hole. So I'm going to move this closer to the camera that we're using from above, just to get an idea of how much I put in here. This isn't really critical because it's not in any way structural. All this is going to do is just form a layer, sort of a gasket around the edge. So the epoxy, which is doing all the work, and again, this is kind of hard to do for the camera. Can you see this? Mm-hmm. Okay. Now, I did a much neater job when I was doing this all alone. And this is a little copious. You don't need to use quite that much. I just had some challenge trying to do this as I'm holding this for the camera. But you want a nice little O-ring looking type of gasket there. And then while this is still liquid, what we're going to do is we're going to insert the nozzle into here until it stops pushing in. Right about there. Now, what we're going to do is we're going to let that again dry for 3 or 4 hours, and then we can feed our epoxy in there in order to get a very nice seal around the edge. But you don't want to try to use this as it's still kind of liquid as a sealant. But you don't have to wait hours and hours and hours and hours. You could probably do this in about 2 or 3 hours. But except for the different parts that I'm using, different core, different guide, the process is the same. And you could obviously keep scaling this up even to much larger tubes. They make and will sell you these spiral round tubes up to 100 millimeters in diameter and about so you could make truly massive rocket engines. And I'm not so sure that you'd really want something that big for anything that you use outside of black rock or, you know, some protected zone, even for testing. But it's nice to know that you could. All right, so you can see now that it's a very creamy mixture with about the same viscosity as the smaller volumes. Turn off the heat. Once you get to that point, you don't gain anything by increasing the temperature. It really doesn't get any thinner. And I'm going to add 2.4 milliliters of the glycerol. Now, if you add even more glycerol, it will get even thinner. But what I found is that the fuel will actually get softer when it finally hardens up. And you don't want a soft fuel grain that could collapse under the load of acceleration or vibration. However, I tested in our centrifuge some samples of the grains, actually with the core cut in them in a large 50 milliliter centrifuge tube. And it was able to withstand 150 Gs for a couple of minutes without any kind of collapse. Now, if you look over here, I'm going to move this over so you can see this. And I am left-handed, so you won't see the inside of the pot, but you'll see what happens when I start to pour this. You can see that I'm right to the bottom of the aluminum ring.
I'll do that again.
I'm going to try to do this without pouring it into the ring.
Good.
Okay. And then what we're going to do before this gets any thicker is I'm just going to extract the ring. I'll hold this down again so you can see the result. You can see how clean it is, and you can see it's nice and flat, and it's at the correct level. So then what we're going to do is I'm going to give this a couple of minutes to cool down because it's really low viscosity right now. And then I'm going to grease up my rod, we'll insert it in there, and we'll give it a little bit of time to cool. So I'm going to go ahead and just steadily put this right down the middle. So it raises, in this case, raises about 1.5 centimeters. And so what's going to happen is once we let that cool a little bit more, then I'm going to pull this out, and then we're going to be able to gasket this just like the other rocket motor. Now I want to talk to you about regression rate. One of the things that's nice to be able to control with your engines is to be able to control how fast the burn occurs. And if you're using this typical mixture, there's not too much you can do other than maybe try to tweak the fuel in the oxidizer a little bit. But there's a much more powerful technique that you can use, and that's by using a catalyst. It's the same purpose for sulfur and gunpowder. And so what you can do is by adding to that 100-gram mix that I described before, which is 65 of oxidizer and 35 of fuel, you can add a single gram of iron oxide. Now this is micron scale particles, a couple of microns across, and it's very easily obtained from Pyrotechnic supply houses like Skylighter, which is a supplier for a lot of our chemicals. And these grains do not get consumed. This is not like in thermite. This basically is just an iron oxide surface that acts to speed up the decomposition of the oxidizer into free oxygen so it can burn more quickly. So as little as 1% of these granules, and if you had nanoparticles, you could use maybe 0.1%, which is what they use in the larger rocket engines like for the space shuttle. But nevertheless, just 1%, so 1 gram to 100-gram mix of this added to the standard mixture is going to produce a much faster regression rate. So let me mix up some of that and I'll show it to you. I'm going to start out with this Orbital. Now you can trust me on the measurements. I'm putting in 35 grams, so I don't know that we necessarily have to see the actual measurement in front of us. Be careful with this stuff. It stains everything. It's a large particle, so it doesn't really get into the air, but when it gets on surfaces, it's a wonderful red dye and actually makes your fuel very pretty. So we just want a single gram of this. Now we're going to put this in the grinder. And now we're going to mix up 65 grams of the potassium nitrate, ammonium nitrate mixture. Again, 61 and 4. So 4 grams of this. Don't need much. Now we'll go ahead and grind up the 65 grams of oxidizer. Now, be careful with this stuff because it just goes everywhere. So we're going to put this in our beaker for doing the blending. All right, put this in the pan. It's just starting to get warm. And we'll start to liquefy this. All right, so this is heated up now to just about the right viscosity. As you can see, it pours nicely. And so I'm going to turn off the heat and I'm going to add 1 cc of glycerin to this. Now what I'm going to do is I'm simply going to pour this onto the aluminum and hopefully make this a similar dimension to the original. That's pretty close. Okay. Now while I have you here, I think we're probably close enough that what I'm going to go ahead and do is I'm going to go ahead and get the rod out of the larger motor before it gets too cool. So now I'm going to extract this, and the trick to doing this is we're going to get the center rod out. Now I have an airflow that allows me to get the rod out without sucking the material back into the space that I'm forming here. So we'll do this rotation to break up any holes or defects. Pull this guy out. Nice. I mean, there's not much debris on here. And you can see inside, formed a pretty good grain in here. Good depth. It's a little bit oblong at the top because I wiggled. But if you wait a little bit longer, you probably wouldn't even get that defect in there, but it's a very smooth hole. So then the next step, I'm going to put on the gasket material here. Nobody's perfect, but it still serves the purpose. A little junky looking, and you can see how the gasket material is around the outer edges. And then what I do is I will press the rocket engine into here until it reaches a stop. That spreads out the gasket material, make sure that I have a good seal. Now, what happens if you actually want to slow the rate of the rocket burn down? Now, why would you ever want to do that? Ever heard when they were launching the big rockets, like say the space shuttle, that when they ignited the boosters and began to accelerate it upward, what would happen is you needed to get away from the Earth's gravity. It's always a taxation that you're paying because you have to first lift the rocket before you can get it up and accelerate it. And so they want all the power they can initially. But then eventually what happens is as the rocket gets going faster and faster in the lower atmosphere, you develop a lot of aerodynamic resistance, and that produces a lot of structural load on the rocket. And so what they'll do is they will throttle back once they get to close to around Mach 1. And the idea being that we'll get through the lower atmosphere at a reasonable level of rate of rise, and we'll accelerate very slowly. And then once we get to the thinner air, we then want to throttle up. That's actually when the Challenger disaster happened, was when they went to 100% throttle. It had nothing to do with the main engines, but it was just at that time, if you listen to the recordings, that the disaster occurred. Nevertheless, you can't really do that with solid rockets. All you can do is either use different rockets or additional rockets or multiple stages that have more or less rockets in each stage. But there's another application, and that is if you wanted to build a rocket engine that was not made to just thrust as fast as you can. You're not building an RPG, you're not trying to boost something up in 1 second, and you're worried about the structural loads. You might say for gliders, be able to take a large glider and rather than putting an E-motor on it or being able to try to toss it off of a ridge, you could put a small rocket engine on it that would have a relatively low thrust for a long period of time, 10, 20, 30 seconds. And in order to do that, you want a very small aperture nozzle, much smaller than the ones that we've been using, and you want a much lower rate of burn, regression rate. The way to do that, as I described before, is changing the oxidizers. So rather than speed it up by adding a catalyst, we're actually going to slow it down by adding more of a different oxidizer, specifically ammonium perchlorate. So in the original mix, we used 65 grams of oxidizer, 61 of the potassium nitrate, 4 of the ammonium nitrate. In this case, what we're going to do is we're going to use 65 grams of oxidizer, but we're going to make 15 grams of that ammonium perchlorate. Otherwise, it's an identical mixture to the first mixture we made up. We're just changing the oxidizer ratios a little bit, and you'll see what happens when we demonstrate this. So let's go ahead and make up a mixture of that. So we're going to start out with 35 grams again of the sorbitol. So 35 grams of sorbitol into the sugar grinder. Now we're going to be doing the oxidizer. And in this case, instead of doing 61 and 4, we're going to replace part of that 61 with the ammonium perchlorate. But I think we're going to start with the potassium nitrate. Now the ammonium perchlorate, we want 15 grams of this. And then finally, don't forget, the ammonium nitrate, 4 grams of this. bring us up to 65. Put the oxidizer in our mixing, blending beaker and our sorbitol. Same routine. And we'll add this. Okay, so now what we're going to do is I'm going to add the glycerol, 1 cc. That's pretty similar. So those are pretty similar in size. I'm going to let this cool over here. And then while these are cooling, what I'm going to do is I'm going to go ahead and show you how to finish up these rocket engines. They've had enough time that the gasket material has firmed up. And so what we're going to do is I'm going to mix up some epoxy and we're going to inject it into the gap. So I'm going to start out with one of my cups and we're going to mix up that standard mix of 25 and 15. Now that this is mixed, we're going to draw this up in a syringe. And similar to what we did when we built the bottom, we're going to fill this up using a short industrial non-beveled needle to do the epoxying. And so I'm going to put this down here very carefully and all the way to the bottom so I don't trap air. And then I'm going to inject the epoxy and let it sort of slowly rise and spread around the periphery so I don't trap any air. That's pretty good. Now if I can carefully bring this over, you'll be able to see. I could probably put another ½ milliliter in there, but basically you get the idea. So what I'm going to do now is I'll fill the bigger motor, same idea, and it's easier. Again, everything is easier the bigger you get. So bring this over here like this. I'll finish up this syringe and then we're going to add some more. This is going to need a lot more. So then you just insert this down to the level of the epoxy so that again you're not trapping bubbles. And as you inject it, you'll see that it flows around the edges, around the sides. Moving the needle just speeds the process, but it's strictly not necessary. That's pretty much it. So then we just let that cure. And by tomorrow we have a very hard epoxy-based ring that will retain the nozzle. And this motor is done. Finally, ways to ignite it. You can use an E-match or an electric resistance element that basically burns and starts off a pyrotechnic mixture. Or you can use a fuse. And if you're just starting out, a fuse might be the easiest way to do this. Now there's a bunch of different types of fuses. There's rapid and slow burning fuses. There are what are called cannon fuses. This is a type of fuse where the burn stays inside of the tube. It doesn't produce a lot of heat outside of it. You don't want to use that. This is a very typical type of fuse. It burns at a rate of about 1 centimeter a second or about 1/2 inch a second. Produces a pretty hot flame, and I've found with my engines pretty reliably will start the engine by simply inserting this to the bottom of the central core and lighting it. But if you want to enhance the performance, you can make the fuse a little hotter by adding to it a little bit of a fast burning fuse. This is a very hot white fuse, and this will burn in about 1/4 of a second. And simply by tying these together with a little bit of thread, a little nylon thread, this is small enough to be able to fit in the nozzle and will add additional heat without having to do anything chemical. Now that's nice, but if you have a very narrow nozzle, you might not be able to get this in here, and it does take a little bit of time. And so another thing that you might do, especially if you're going to make a lot of them, is you might enhance the properties of the fuse by adding some hot burning pyrotechnic flash powder to the outside. The trick to doing that is actually very simple. Get some contact cement or even PVC cement will work. And you simply take a length of fuse that will be convenient to insert into the motor and have enough so you can run. And so I took these little 20 centimeter, 7-inch length of fuse, cut it, and then I marked it about the depth that it would have to go into the engine. And then simply taking this contact cement, you dip it in to the mark and pull it out. Now, if you wait a few seconds, what will happen is this will begin to drip off, and then after about 5 or 10 minutes, it will stiffen up enough that it's not going to run anywhere. And what you'll end up doing is you'll end up producing a very sticky, rubbery surface as the solvent dissolves, and this then can adhere to the flash powder. Now, the flash powder is a very simple mixture. I'm not going to mix it up for you because it's really simple. It's a 50-50 by weight mixture of aluminum powder and ammonium perchlorate. That's it. You blend it up. You can do it by weight. You blend it up into a little cup, and this powder then will stick to the outside of the wick and form that extra additional heat that you're going to want during the process. Now, I'm rushing this a little bit. I'd let this sit normally for a couple of minutes. But if you simply take the powder in a tall cup like this and just jam the wick in here, you can roll it around. Nothing neat about this. But what will happen is it will attach to the surface and then just flick off the extra like this and set this in another cup and let it dry. Let it dry overnight. It'll be fine. That's what I did to these wicks here. Now, least you think this little tiny layer isn't going to make a difference, let me show you how powerful this mixture is. I'm going to take a very small quantity of this flash powder and I'm going to go over behind me onto this fire brick here. And I'm going to take a small quantity of the flash powder. That's not a small quantity. Not very much. Let's say this much. And I'm going to put this down here like this. And then I'm going to show you what that will do. Hang on. 1, 2, 3. Blinding and very, very hot. And that's what you need to get those hot aluminum particles into the inside of the engine in order to get the fuel started. And once it's started, it's stable. And so using a wick technique like this is great. If you do an E-match, you can do the same sort of thing. You can use the resin and you can add some pyrotechnic powder to it and again, heat it up to make the engine starting a lot more reliable. Now, before we close, and I'm going to tell you that what we're going to do is we're going to go outside and we're going to test these different mixtures to show you what the regression rate is. I want to thank you very much for watching. This is a lot of fun. Rockets, kind of like the smoke bombs, kind of like explosives, kind of like the stuff you do that's high energy, is just a lot of fun to play around with. And once you know how to do this stuff, you can then take it from there and apply it to a whole bunch of different purposes, like launching gliders, like using it to propel rockets, as well potentially drive a magnetohydrodynamic generator. So please, if you can help us out, we're trying to reach 500,000 subscribers by Christmas time, and we're close. And so if you do subscribe, even if you don't want notifications, please, it's like throwing money in the guitar case of a street musician. It's the way that you show a thanks for the time and the effort that we put into this, and we really appreciate seeing those numbers going up. So let me go ahead and cut these things out, and then I'll go ahead and bring this outside, and we'll do the testing. And please, if there's anything about this very long video that you have questions about or you want to comment about, put it in the comments below, because I do read every single one of them. And I try to answer as many questions as I can to help clarify anything that I might have skipped or didn't cover very well in the video. And it also gives us ideas for other videos. Let's go outside and see what this does. So this is going to be the standard mix, the first that we mixed up, and the medium speed. You can see it makes a lot of gas. And you can see the slight purple in the flame from the potassium. All right, so this is the fast mix with the iron oxide catalyst. And now this is the slow mix with the ammonium perchlorate substituted for some of the potassium nitrate. Okay, so that you can see that there is a clear difference in the regression rate between the different formulations. And keep in mind that the samples that we tested were all about 150 millimeters long. And in a typical rocket engine, the distance between the center of the grain and the outer wall is only going to be a few millimeters. And so the burn times for a typical rocket are going to be proportionately shorter. Now tomorrow what we're going to do is behind me we're going to set up the test stand and we're going to run the motors that we built tonight. You'll get to see how well they perform. You'll get to get an idea of just how much power they can produce. And we'll post that video a couple of days from now. So I'm going to wish you a very Merry Christmas, a very Happy New Year, and you take care and stay safe. Good night.